Our new unit today on dealing with math and numbers in science, or at least in our science class. So these first few topics are going to be, should be a review. There are things you probably visited in your high school math class before, but we'll kind of go back and revisit them just to make sure that everyone's on the right page in terms of being able to use these numbers, because we do have to use this sort of numbers, the scientific notations, in the classes that or in the unit we're about to do next. So it's one of those pieces we gotta double check what it is. So talking about scientific notation today, and scientific notation is just a way of writing either very large or very small numbers in a much more compact way. So we don't have to write all of the zeros that shows up in numbers. So the numbers, the couple examples there on the board or on the screen there, just so you take a look at it, they'll have kind of a similar sort of a format to them. There's always a number, and then there's an x, which means times, and then there's a 10 to an exponent. This is what we see in scientific notation. It's very similar to what math teachers typically call exponential notation. It just has one additional rule to it to make it a little bit more consistent in how we write it across the board. But it's the same basic idea. So those ones are examples that I put on there just to make sure that you know how to read those. You'd always read it as the number out in front and then times 10 to the whatever power. So we've got 6.02 times 10 to the 23rd, or 8.3 times 10 to the negative 8th, or minus 8th if you want to call it that way. But you just kind of read it from left to right. You don't read it as an x. You read it as times 10 to the, and you'll hear us say that kind of a lot as we go through these. So why do we even bother doing this? Well, it turns out that science deals with lots of numbers that are either really, really large or really, really small, and it just saves a lot of errors, saves a lot of time and space on your paper as well. So a couple of examples of just crazy numbers on the screen in front of you, that a single drop of water contains, I can't even say that word, let's see, 1,000 million, billion, trillion, quadrillion, quintillion, 1.39 hexillion. I don't even know if that's the right number for that. Just a ridiculous large number of zeros there. And it's easy to misplace how many zeros you're talking about. But there's a ridiculously large number of atoms or molecules of water, even a single drop. Similarly, we can talk about really small ones. Like if you want to talk about how much gold weighs, well, we could talk about grams, like the dude's got a pile of, I wish I had that gold dust in his hand. But if you talk about a single atom of gold, again, I don't even know how to say that number, 0.000000. I lost them all, 32706 grams. It's incalculable. It's unimaginable how small that number is. We have no kind of way of discussing what that is. So we write these kinds of numbers in scientific notation. So you can see the two equivalent numbers down at the bottom. So the top one, the number of atoms or molecules of water in a drop, is 1.39 times 10 to the 21st. There's a whole bunch of zeros after there. Or the weight of a single atom of gold is 3.2706 times 10 to the negative 22nd grams. That's a lot of zeros that should be in that number. It's just ridiculous how many there are. So again, it saves a lot of space. It saves a lot of misunderstanding. You don't have to try to pronounce out these crazy weird numbers in terms of trying to figure out what they are. We also don't just use these in chemistry. These are used across math, and not even just in math, but we can talk about populations of the world. If you've ever heard someone talk about there's 3.5 billion people, it's actually a type of scientific notation, believe it or not. As soon as you say billion, that word, that's a times 10 to the number that's after it. So anyway, mass of the Earth, really big number, right? 5.97 times 10 to the 24th kilograms. It's ridiculous. Distance of the sun. We could talk about the national debt. That number just astounded me, what that national debt was. I had forgotten it was so big. I guess maybe I didn't want to think about it. So that actual value there is crazy. 1,000 million, billion, 19 trillion, $19.5 trillion, plus 2.38 times 10 to the ninth, a couple of $1 billion every day. Ridiculous when we start talking about numbers like economies or populations. Like I said, astronomy has lots of big numbers in it. Or like I said, in chemistry, we're talking about lots of really, really small numbers. So it makes a difference to us to be able to kind of shorten that up a bit. It's a lot more convenient for us. So the basic rules, again, this is a type of exponential notation, so you always have the same sort of format. There's a coefficient out in front, a number, and then there's times the base, which is base 10 in this case, and then to the exponential power, so whatever that is. So you have a times 10 to the b. The first number is always going to be the coefficient. The big difference between scientific notation and generic exponential notation is that in scientific notation, that number has to be between 1 or 1.0, and it has to be less than 10. You'll never have a two-digit number there. It could be 9.99999, but you would never say 10.5 times 10 to the something. So you've got to make sure that that decimal place, when you put it in there, is always between the first and the second digit. So 256 would have a base of 2.56. You put that decimal place right up against that first digit. The base is always power 10. We're not going to use any other weird bases. You could. Why would you want to do that? some sort of math nerd probably has figured out a way to do that, but I don't want to do that. So you're always going to use a power of 10. The reason why we use power of 10s is because 10s are decimal places. So if we're saying times 10 to the first, 10 to the second, that's 1 decimal place, or that's 2 decimal places that we're moving it over. And again, for us, if you're doing that number 256, when you make it 2.56, you've moved the decimal place over 2 spots, so that becomes 10 to the second. The number of spots that you move it is the exponent. Take a look at a couple of examples of this. So again, the rules, you got to put that new decimal place whenever you're shifting something between the first and the second digit, and then count the number of decimal places that you're sliding that decimal place over. Again, if there isn't one there, it's assumed to be at the end of the number, so you just kind of do the little bounce count to figure out where it's going to be. And then the last thing is that you would drop trailing zeros. So if there are some weird trailing zeros, like you're talking about a number 950 million, and there's just a bunch of zeros hanging out, you're allowed to drop those. So here's the examples that we're going to work through. I'm going to work through the first one slower, and then it's a good idea to pause and you do the other 3 by yourself. So we'll take a look at that first number, 6,235. So we start by writing the new coefficient. We move the decimal place between the 6 and the 2, so it's going to look like that. The second thing that we do is we figure out how many places have we moved that decimal place over. And it started after the 5, we move it up 3 spots. So that means my new base and exponent is going to be times 10 to the third, because I moved it over 3 spots. So now would be a good spot for you to hit pause and see if you can work out those other 3 examples that are on there. And then I'm going to work through them here, or show you what the answers are anyway, but I won't work through them quite the same way. So here's first, the way I have this set up is I'm going to show you the 3 coefficients, and then I'll go back and add the 3 bases and exponents afterwards. So here's your coefficients to make sure that you're clear on where you're moving that decimal place to. Again, it always has to be between the first and the second digit, because our coefficient here has to be a number between 1 and 9.9999. So we've got 9.4, 5.2, 8.7, and the rest of the values on there. Notice how I only dropped off the trailing zeros. You left all the other digits there. You're not allowed to kind of like round in the middle. All right, exponents. So in that first one, we moved it over 6 spots, 3 zeros, and the 3, 5, 4 gives you a total of 6 decimal places that you moved it over. The 5.2, we really only moved it over 1 spot. It's kind of a weird number to write in scientific notation, but you can. So it would be 5.2 times 10 to the first. Weird, right? I know, but it's possible. And then that last one, we moved that a whole bunch. I see a set of 3 zeros, another set of 3 zeros, so that's 6 spots, plus another set of 3, that's 9, 10, 11. Wow, that's a big number. Yep, 0.87. Geez, can't even talk today. 8.728, and then 11 decimal places times 10 to the 11th. All right, we can do the same thing with really small numbers. That last page all had really big numbers, so they were in the millions, thousands, billions, etc. We can do the same thing with little tiny numbers that are in the tenths, hundredths, thousands, millions, billionths of a spot. Yikes. Same ideas. Again, the coefficient has to be between 1 and 10, or less than 10, 9.99. Again, we would use that decimal place between the first and second non-zero. So in this example that I have here, 0.000862, you have to put the decimal place between the 8 and the 6. Next thing is when we're counting over now, because we're replacing decimal places, we can't use positive exponents. We have to use negative exponents. We're moving the decimal to the right this time. So we would say in the one example that I've got there, you're moving it over 4 spots, so it's got to be to the negative 4th power. So our final answer here would be 8.62 times 10 to the minus 4th. So whenever you see a negative exponent in a scientific notation, that's telling you it's a tiny number. It's a number less than 1. So here's some examples. So in terms of what you are going to do on here, again, the rules, you're going to place the decimal point between the first and second non-zero numbers, so that coefficient is between 1 and 9.99. Again, the second thing you're going to do is you're going to be counting over to see how many spots you're moving that decimal place. This is your exponent, but make sure that you're going to put it as a negative exponent. And now in this one, a little special rule here. You're only allowed to drop leading zeros. You cannot drop zeros at the end of a number. So let's take a look at this one. Here's the example I'm going to have you do. Kind of same thing. I'll work this one out and then let you guys do the other 2 that are on this page. So with this one, 0.007495, I move the decimal between the 7 and the 4. So now I've moved it over a couple of places in terms of 3 spots from where it originally began. So that's kind of what I'm taking a look at. I'm moving that decimal place to the right, so that means I'm going to have a negative exponent to it. And then it becomes 7.495 times 10 to the minus 3rd. Again, I'm allowed to drop the leading zeros. I don't have to put those in there. Mr. Santana just walked by, so I'll have to say hi to him, right? Hi, Mr. Santana.
So you got like
You're famous on YouTube now. There we go. So the second and third examples in terms of what those are. Same idea, move the decimal place over, and then count how many spots you moved it, and then you're only allowed to drop leading zeros. So hit pause, see if you can do it on a piece of paper, and then I'll come back and do them in about 3, 2, 1, go. Okay, here's the coefficients for it. So that one becomes 3.50. Remember, you can only drop leading zeros. That 0 at the end, you got to leave it in there because it's going to tell us something about how good that number is. We'll get to that later on, but again, the rule here, only drop leading zeros. We never drop trailing zeros in very small numbers. Again, more on that in a later lesson. This bottom one, it's going to end up being 9.8. Lots of decimal places to move that over. Then the next part is count it over. How many decimal places did you move it? The 3.50, I only moved it over 2 spots, so it's to the negative second power. That 9.81, man, I moved it a bunch. 3, 6, 9, something like that, 10, 9 spots. There you go. It's even hard to count just by looking at it. So 9.8 times 10 to the minus 9th. If you take a look at those exponents, the bigger the exponent, the smaller the number. All right? That's more zeros that you're moving it over. So the bigger the exponent, 10 to the minus 11th, 10 to the minus 20th. Those are ridiculously tiny numbers. All right, I think the last couple slides I've got here is to talk about calculators. Every one of you is going to have a slightly different calculator. I've got some in my classroom that you guys can use, but you probably have your own, or you should have your own. And you probably want to kind of fast forward this to your type of calculator. They're all a little bit different how they show scientific notation or what button you use to enter scientific notation on a calculator. So this should help you kind of get the tour. Bring your calculator to class, and I can kind of show you where some of these are. But like I said, they're all different. So I can't do every single possibility, but it'll give you some ideas of what they are. The Casio models are kind of nice. The newer ones actually have, like this one right here, has that times 10 to the x button, so that's a pretty obvious one to use. Older Casios and a couple of other different brands that I've seen have a button like this that looks like EXP, and that means the scientific notation. So if I wanted to enter 3.45 times 10 to the 6th, I would type in the numbers 3, 3, and then the point, and the 4, and the 5. And then that times 10 to the part, you can just hit this button, the EXP button, or the times 10 to the x button. And then all you do is enter the exponent to it. So it's kind of nice. You don't have to hit the multiply button. You don't have to hit the 10 and the caret and all that other stuff that sometimes your math teachers teach you to do. There is a button that will take care of it for you on your calculator. Big caveat, big warning here is that if you're trying to use a negative exponent, really important that you find the plus minus button, the negative button. It is not this button. This is the minus button, and that's not the right one. That means subtract. That doesn't mean negative. So there'll be another button somewhere else on your calculator. So just to kind of take a look around, hunt for it. Usually like a minus in parentheses, or maybe it says plus/minus, and that's the one that you want to use. Some other kind of calculators, if you have a TI model, TIs are the worst because it's actually kind of a two-step process. You want to look for these little tiny EEs, and it's on the button just above the 7 on most of the TIs that I've seen. So here it is right here. You can see it on that one. That's actually a graphing calculator down there. But you want to look for that little EE letter, and that means scientific notation. But because it's printed on the calculator body, that means it's a second function, kind of like the shift key on a keyboard. So you have to hit the second and then that key, and that'll get you the scientific notation. So again, it's a little bit bizarre in terms of using those, but like I said, come into class and I'll show you what that looks like. Here's a good example on the TIs, what the negative button looks like as opposed to what the minus button looks like. The minus button will be over by the plus, minus, multiply, etc. The negative or the plus minus button will be somewhere else in the calculator. And then the last one, if you're using your phone, which you can do at home, which is fine, but you cannot use it during class, so be careful with that. Turn your phone sideways. If you have it right side up, the calculator is the little mini calculator. Turn it to the left, right, horizontal, and you can usually get the extended keyboard. I'm not sure about Android or Samsung, Galaxy phones, that kind of stuff. I don't have one, so I'm not quite sure, but you might want to play around with it. But again, you're kind of looking for that EE button, and it works kind of the same way. You just don't have to hit the second on these. But that's how you would do it on those calculators. Okay, the last thing, output. The way it looks on a calculator screen looks a little funky. When they made the little screens on a lot of the older calculators don't have a lot of characters to them, so they had to kind of shorten it. To do the 10 and the little exponent was really difficult, I guess. So they shortened it down to just have an E in the display on a lot of them. Some of the newer ones actually show it all out. So if you've got one of those, you're lucky. But if you've got one like mine, it's just going to show an E there. And again, that E means times 10 to that. They just shortened it down and replaced it with a small, funky capital E. So what I would suggest that you do is you write your numbers in in your calculator, practice a little bit, and get used to what your calculator looks like. And then every time, use the same calculator. Again, last thing I should say, sorry, not again, but your calculator is going to show you a funky output like that. You're not allowed to write that on a piece of paper. So on a math test or in a class or a lab or something like that, you're not allowed to do that. You have to translate from calculator to actual true scientific notation. So if you wrote 1e minus 4, I'm going to mark it wrong because that's not really scientific notation. That's just a calculator display. So be aware of that. So there you go, a review of scientific notation, kind of why we do it, how we do it, and then some of the different ways that we have to enter it into calculators and some of the output to it. So I hope it kind of brought back some memories of math class and days past. I'll see you in class tomorrow. Have a good one.